All right. Afternoon. How was lunch?
It was good. How
Good.
was yours?
It was good. It was good. I made it. Any questions on homework?
I have
I also have one.
What you got? Ladies first.
number 10.
All right. Number 10. Was it proof? It was. Okay. So I will give it a shot, see if I can draw it real quick. So you got a right triangle. We know it's a right triangle because it says that these two lines right here are perpendicular. And we got V right here. So that's V. And then this is X, Y, Z. You are told that VY is perpendicular to YZ. So we can immediately claim that that's a right angle, right triangle. And you're told to prove that VXZ, so we're trying to prove that VXZ, I should write that at the bottom, VXZ is obtuse. So definition of obtuse, greater than 90. So here's how this would work. We know that this angle right here, which is VXZ, has got to be greater than angle Y. Why can I say that?
Because it has it's equal to angle Y and Z added together.
Right. Well, the one theorem we says that the remote angle is larger than either one of the, or the one external angle is larger than either one of the two remote angles. So I can say that immediately, and then you could say that the measure of angle Y is equal to 90, and then therefore you could say that VXC has to be obtuse because it's bigger than 90. That's how I do it.
Okay, thank you.
Yep. Anybody else?
Number 11.
Yeah, that's an ugly one, isn't it? All right.
Yes, it. Yeah.
So this one just takes steps. The actual logic behind it is not too bad. It just takes a bunch of steps to get there. And then this one extends. So we got 1, 2. That one right there is 3. And this one right here is 4. And you're asked to prove that the measure of angle 1 is bigger than measure angle 4. Bigger than the measure of angle 4. Okay. So you can start it many different ways. I'm going to start it with angle 1. I know that, and I did it again. I wrote that as, I should have wrote that as my last. So imagine this is down here. Okay. I'll draw a line. I'm going to say that the measure of angle 1 is bigger than the measure of angle 3. Why can I say that?
Theorem 6-1, whatever it was. Like
same thing we just used. Then I could say that the measure of angle 3, this one's harder to see, is bigger. Did I label this wrong? This is 2. I'm sorry. 2. So the measure of angle 2 is bigger than the measure of angle 3 for the same reason. This is the external, that's the remote. And then I can lastly, I can say that 3, measure of angle 3 is equal to the measure angle 4 vertical angles. And then a little bit of substitution or transitive property, and we would get to the final thing. So let's see. How do I get a 1 here? Well, we're going to start off with this statement here. So I'm just going to do a whole bunch of substitutions for that statement right here. So I can write the measure of angle 1 is greater than. Now I'm going to substitute for angle 3. So for angle 3, I'm going to put angle 4, and I'm done. I didn't even need that statement right there.
Well, I think you're supposed to, for your first one, it should be measure of angle 1 is greater than measure of angle 2 because 3 is too remote.
Yeah, you're right. So 3 is 2. Okay, there you go. That's how I would do it.
Okay, thank you.
Anybody else? Okay, here we go. Going to call up the answers. Wow, this is a lot of work. So this is a whole bunch of yeses and nos. So number 1, I'm going to go through A through F. No, yes, yes, no, yes, no. Okay?
Can you repeat that one?
No, yes, yes, no, yes, no. Number 2.
Okay.
No, yes, 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 no, no. Number 3. No, no, yes, yes. Number 4. Yes, yes, no, no. That's way too many yeses and nos. Okay. Number 5, J is 2, K is 1, L is 4, and M is 3. Number 6, the reasons. I'm just going to give you the reasons. Given, CPCTC, segment addition postulate, property of inequality, and substitution. Number 7, well, they don't start off with given. They start off with vertical angles are congruent. Number 2 is angle addition postulate. 3 is property of inequality, and 4 is substitution. Did anybody notice that the question number 8 was like the one we did in class?
It was, yeah.
Yeah, you should have. I just changed it around to give you a hand. 8 and 9 are done basically the same thing. You simply say that the 2 parts, either on 8, it's going to be a whole bunch of segment addition postulates. On 9, it's going to be angle addition postulates. And you just, 8 is done exactly like the one we did in class. Add those 2. 9, you simply just call out that if you add angle SOT to both sides of that given, and then that's what defines ROT and SOV. And then we did 10 and 11. So hopefully you weren't, since you didn't ask for 8 or 9, I'm sure you got it right. All right, we good? No one is complaining, so I'm going to go on. Okay. So luckily for you guys, today's a nice, easy day. We'll talk about the quiz tomorrow. Here's your homework for tonight. And like I said, you're going to see that, you know, these numbers are in the assignment itself. So if you don't want to copy them down, that's fine because it'll be on the assignment. So I'm going to move on. All right, so I said yesterday this chapter is on inequalities. It is. However, we take a side step. We don't talk about inequalities today. We talk about our last 2 for the entire year, our last 2 logical results. We've talked about conditional statements. We've talked about converse statements. There are 2 more that we'll talk about this year. They're called the inverses and the contrapositives. These can, when you put them all together, converse, inverse, contrapositive, they can become very confusing. But since you can put this all in your book of truth, and we'll write it on 1 page today, you can keep it nice, neat, and orderly. All right, so last class, we had these 5 inequality properties, pretty straightforward. We'll come back to them after this section because this chapter is on inequalities and geometries. But for today, we're going to talk about the other logical ideals. And these are, we've seen 2 of them already. We've seen the conditional statement and we've seen the converse. In fact, we've had many theorems that were converses of other ones. And I've given you, this was chapter 2 stuff, I've given you statements and asked you to write the converse, and you've done that. So we're basically going to do the same thing, except I'm going to give you 2 new ones today. One's called the inverse, and one's called the contrapositive. And lastly, we'll wrap this up with Venn diagrams today. All right, so this can be confusing. I would say this is on the level of being medium. It's not hard, but it's definitely a medium, and if you don't pay attention, you can get lost. So, you know, I put this more for the other class, not for you guys. So way back in chapter 2 is when we saw conditionals and converse statements. So remember, a conditional statement, an if-then statement. This is the one that I used way back in chapter 2, something like if it's raining, then the sidewalk is wet. It's called an if-then statement because literally it has an if and it has a then part to it. So it's 2 parts. We like to make it far more confusing than it has to be. So instead of saying it's an if-then statement, we say if P then Q to refer to any conditional statement. If the P part is true, then the Q part is true. All right. So we do need to refer back to remember what a converse was. So using this notation, if P then Q, if we talk about the converse, then if you remember, all we do to make the converse is we switch the P and the Q. So the Q comes first and the P comes second. So for instance, this statement, it started off as conditional if it is raining and the sidewalks are wet. If we flip-flop that around, they would say if the sidewalk is wet, right? I'm going to do blue then red. If the sidewalk is wet, then it's raining. That's the converse. Now, I haven't said anything about whether or not either one of these statements are true. We're just talking about the construction of a converse statement. Okay, and this is old hat. So this is, even though I would typically have you write this down in class, I'll leave it up to you whether you decide to write it down or not. Because this should be in your book of truth, how to make a converse, way back chapter 2. Today's class is on the other two, the inverse and the contrapositive. So I'm going to frame both of them like I framed this slide right here. I'll show you the conditional statement, and then here in the big yellow box right here, we'll write inverse, and then I'll show you how it's constructed. Okay? All right, here we go. So back to our if it's raining and the sidewalk is wet, that's our conditional. We have this construction called an inverse. And an inverse, we do not switch the P and the Q, we negate both of them. By negation, I mean we literally put a not in front of them. So if P then Q, the inverse of that statement would be if not P, then not Q. So it's kind of weird the way that we talk about it, but once you do it a bunch of times, it becomes old hat and you become used to it. So the inverse of any statement would be you take the original, the if part, you make it a negation, and then you take the Q part and you make it a negation. So what would that look like? If we negated if it is raining, how do we make that say negation? We would say if it's not raining, then the sidewalks are not wet. Oops, sorry, the sidewalk is not wet. Okay? And that's literally how you make an inverse. Once again, I'm not going to say whether or not these are true or false statements. We're just showing you how you construct the inverse. So I'll give you a moment or two to write that down. So make sure you have this because tonight they're going to ask you to create some inverse statements. The first table that they have you do, it's green tonight for homework. They want you to use the letters P and Q. They don't really explain it that well. This is question 5 through 10, that sort of thing. They're going to give you a couple statements. Just remember this basic, the P is the first statement, the Q is the second statement of a conditional, and then just follow along. You will have to remember what converse was. So if you want me to go back to that one slide to make sure, but converse is if Q, then P. We good to go on this slide?
Yes.
Okay. So one more. It's called the contrapositive. The contrapositive. So same basic statement here. If P then Q. The contrapositive. What it does, it's kind of like the converse. So you see the con in the converse, or con in the contrapositive. It takes the P and the Q and it flips them. But the positive part, well, it doesn't really fit. But if you're contra to positive, then you're negative. So it flips the P and the Q and it makes both of them negative. So you flip the P and the Q and you negate both of them. So if not Q, then not P. So let's see. I'm going to flip the P and Q. If the sidewalk, I got to negate it. If the sidewalk is not wet, then it is not raining. That's how that would be, that construction right there. Look at the homework here. It says write the contrapositive, write the inverse of these statements. Then there's a table that has you writing the statements and then figuring out if the statements are true or false. And that's what we'll talk about next.
Do they have to choose P and Q? Like maybe
I
A
hate
and
it.
B?
Shouldn't they choose two letters that don't look alike?
Yes.
Yeah, and if you ever take what's called formal or symbolic logic course, we might offer it in high school. We're debating whether or not to offer it. But if you ever take a formal logic class, you're going to be dealing with P and Q all the time. I don't know who made that decision to use P and Q, but it wasn't me. Okay, so that's the contrapositive. If not Q, then not P. And you know, I've been doing this a while, so it's old hat for me. But when you get used to it, these are pretty memorable. But since you get to use the book of truth, then you can always have in your book of truth. All right, so what's this all about, right? Sounds a little confusing. Well, it turns out that we have some consequences for this. Now, if the, pun intended, if the if-then statement is true, and remember in the geometry book, all the theorems are if-then statements, or they're biconditional. So, but they're all, we accept them or we prove them to be true. So we're going to look at the consequences that if the conditional is true, what could happen. All right, if the if-then statement is true, it turns out that the converse statement might be true. It's not always guaranteed, right? If you make the converse to the statement, and we will do a better example here. If you make a converse statement to the, if it is raining and the sidewalks are wet, what turns out that might be false. So if the sidewalks are wet, then it is raining might be true, it might not be true. Remember, the sidewalks could be wet after the rain stops. So, you know, certainly if the sidewalks are wet, it might be raining, but it's not guaranteed that it's raining. So it's not always true. Converse statements are not always true. And remember, we're going to predicate all of this on the fact that the original conditional, the original if-then statement is true. If the original statement is true, the converse could be true, it could be false. Turns out that the inverse statement, if it is not raining, then the sidewalks are not wet. Well, the sidewalks could be wet if it's not raining, right? So they also could be dry. So it turns out that the inverse statement is also, it might be true, it might not be true. But an interesting thing happens with the contrapositive. If the sidewalks are not wet, then it is not raining. That's 100% true. So it turns out that the contrapositive is always true if the original conditional statement is true. And that's really what this slide is all about. The slide is about showing you that if the if-then statement is true, then the contrapositive statement is always true. The converse or the inverse might be true, but the contrapositive is always true. Now be careful what I just understand what I said there. I said that if the if-then statement is true, then the contrapositive is always true. If the if-then statement is false, well, the contrapositive could be true. But if the if-then statement is true, the only one that must be true is the contrapositive.
So then if the contrapositive is true, then is the if-then statement true?
Ding, 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 100 points for you, yes. And I will finish the class talking about that particular, I'm midway through the class, we'll talk about that. That is true. So if the contrapositive is true, then the if-then statement is true. Vice versa, that's biconditional. Okay, everybody got this one down?
Yeah.
The issue is the converse and the inverse. It doesn't matter if the if-then statement is true or false. You always have to look at the converse and the inverse. The contrapositive, right, will always be true if the if-then statement is true and vice versa. All right, so this is dependent upon whether the if-then statement is true. All right, so let's see how this looks like in geometry. So here's a statement. If two lines intersect, they are coplanar. True or false?
True.
That is a true statement. So if that statement is true, what do you immediately know about the contrapositive?
That if two lines do not intersect, then they are not coplanar.
No,
that would be
No,
the
if two lines are
contrapositive.
not coplanar, then they do not intersect.
yes.
But we don't even need to worry about what the statement says. We know that the contrapositive is true. So if the if-then statement is true, then the contrapositive is true. But we don't know, I mean, we could immediately write that down as well too. What we don't know is whether the converse or the inverse is true. So in order to figure that out, we gotta write it down. So somebody give me the converse to that statement.
If two lines are coplanar, then they intersect.
So is that true or false?
Oh,
False.
False.
So if two lines are coplanar intersectable, they could be parallel, they'd be coplanar. So we would say that it's not necessarily false, but it certainly isn't true, right? So yeah, not always true, okay? It could be true, I mean, if they do intersect, right? But they could also be parallel and then they wouldn't be true. What would be the inverse of the original statement? So that would be the if not P, then not Q.
If two lines do not intersect, then they are not coplanar.
True or false?
False?
Yeah, that one's false too, because think of parallel lines. If two lines don't intersect and they are not coplanar, well, parallel lines are coplanar. So that one would not always be true. Okay, so you just have to be careful with the converse or inverse. You can't assume anything simply because that the original conditional is true. But what you can always be sure of is that if the conditional is true, the contrapositive is always true. I don't even need to write it down. By the way, what would be the statement for the contrapositive?
If two lines are not coplanar, then they do not intersect.
And we are guaranteed that that's true simply because the conditional is true. So if two lines are not on the same plane, they don't intersect. By the way, what do we call that two lines are not on the same plane? What do we call that? Do you remember?
Skew.
Skew lines. There you go. Okay, so that's how some of the homework will be tonight. They give you a mixture. I'm looking at some of the questions. They give you a mixture of a little bit of algebra and geometry, and then ask you to write the, the three statements: the converse, the inverse, contrapositive, and figure out if they're true or false. So questions 1 through 4 is just write the statement. Questions 5 through 10, write the statement and figure out if they're true or false. All right, one more time. Here's another example. If two angles are congruent, then they have the same measure. True or false?
True.
Okay. So immediately, what can you say?
That the contrapositive.
Immediately. I don't even need to write it down. Well, obviously, if they ask you for homework, you got to write it down. But I know the contrapositive is true. What would be the converse to this statement?
If two angles have the same measure, then they're
Okay. So if two angles have the same measure, true or false?
True.
True.
That was true. So here's an example of where the conditional is true and the converse is true. Once again, you're not guaranteed that the converse is always true or always false. You have to figure it out individually. What's the inverse to the statement?
If if angles are not congruent, then they are the same.
Yeah, if two angles are not congruent, then they don't have the same measure. True or false?
True.
Turns out that all of these are true. So here's an example where literally every statement is true here. The previous one that we did, remember, and I'm going to go back. The previous one we did, notice we got a true, false, false, true on this particular one. But on this one, we get every single one of them is true. Oh, by the way, the contrapositive would be what?
if two angles do not have the same measure, then they are not congruent.
Yeah, there you go. Okay. So there's two good examples of converse, inverse, and contrapositive. Any questions? Okay.
No.
Last one, because we're in District 49. Let's see if we can do this one. All right, McKinley, you got the first one. What's the converse to that? Oh, by the way, you got the conditional. Is the conditional true or false?
The conditional is true.
Heck yeah, we're in District 49. They'll call a snow day if they even think it's going to have a blizzard. All right, Anna, what's the converse?
If there is a snow day, or if D49 has a snow day, then there is a blizzard.
Okay, true or false?
True. Or
So
not always.
yeah, not always true and false. Either one is fine, right? Because we can certainly have a snow day when there's not a blizzard, like it stops snowing and there's 4 feet of snow on the ground. Well, there's not a blizzard, but we certainly are going to have a snow day. All right, Jack, what's the inverse?
If there is not a blizzard, D49 will not have a snow day.
If there is not a blizzard, then there's not a snow day. What do you think? True or false?
False.
If there's not a blizzard, then there won't be a snow day. And we just said there will absolutely be a snow day, even if there's not a blizzard. So even if it snows 1 inch, that's not a blizzard. We still might get a snow day. Okay. All right. Who wants the last one? Contrapositive.
Me.
All right. True or false before we even write it?
It's obviously true.
It's got to be true because the conditional is true. I don't even need to think about the logic. It's guaranteed to be true because the conditional. And then what is the contrapositive?
The contrapositive is if D49 doesn't have a snow day, then there is no blizzard.
So if we are in school, you can be guaranteed there ain't a blizzard going on. So that's got to be a true statement. All right. Well, there you go. There's a real world example right there of using that. So sarcasm, some people think that's fun. If you like that sort of stuff, then you probably want to be a lawyer. Because that's literally what they do in order to prove things. They gotta have to prove things logically. All right, so we're gonna move on to a new thing, and I don't know how many of you have seen this before. Hopefully, most of you. I'm sorry, I forgot this. This was the thing I was talking with Jack about. So it turns out now we have a second way of solving proofs or doing proofs. Before this, we always, in order to prove thing, well, we had to start with a given and arrive at the proof part. Well, we just showed that in order if you're given an if-then statement that is true, remember that's what we're trying to do in a proof, that it also means that the contrapositive is also true. So sometimes in geometry, it is easier to prove the contrapositive than it is to prove the conditional. And wouldn't it be nice if the book gave us an example of this? And the answer is they don't. Yet in a couple sections, I don't know if it's the next section or the section after this, we will actually do something called a proof by contradiction. And so we will either prove a contradictory thing or we will prove the contrapositive. So that's kind of moving forward, something that we will do in the future. I wish the book had done it right now to show you an example where if you prove the contrapositive, then the if-then statement is true. But unfortunately, we don't. So that's the where I will leave it at that, and then more to come on that one. Okay, so the second new idea, hopefully it's not new to you, is something called a Venn diagram. So both of those are the same person. They certainly don't look like the same person, or Wikipedia is being wrong on me. But those are both from Wikipedia, and they claim that they're both of this guy named John Venn. He was a British mathematician, philosopher, lived in the later half of the 19th century into early 20th century. And he came up with this thing, which is a pretty nifty thing. In fact, it's so nifty that almost every field of study, to include the English, language arts, philosophy, they use these things. And these things we know as Venn diagrams, named after John Venn. Okay, so here's a Venn diagram. People who like math and people who like Oreos. And I am smack dab there in the middle because I like both of those. All right, one thing about this Venn diagram, it is an improper Venn diagram. It's actually missing something. And most of the time you see Venn diagrams, they look like this, and I wanted to show you this and then point out the correct way of making a Venn diagram. Does anybody know why this one is incorrect?
Because there needs to be a third circle.
There could be a third circle, but in this case, no.
Isn't it because one, you're not the only person who likes math and like Oreos?
Well, that's true. Okay. No, it's actually missing something. So, all right. I didn't know if any of you guys had done actual Venn diagrams before. So write this down somewhere. There's just basically a couple key points here. Venn diagrams are something in the field of math called set theory. Set theory are a branch of mathematics that deals with sets of things, collections of things. And the thing that was missing from that Venn diagram is what's called the universal set. Sometimes it's referred to as the big rectangle. So the big rectangle, which is supposed to be in every Venn diagram, defines what is the population. So the population of things that inhabit the Venn diagram has to be defined from the start. I didn't define that in my previous Venn diagram. I didn't say, well, this is a collection of, I don't know, dogs and people. And in the collection of dogs and people, we have this subset, right? And so subsets are what the little circles are. But yeah, the rectangle is what was missing. Sometimes they're drawn with rounded corners, but most of the time they're drawn with rectangles. Okay, so to make a Venn diagram, it's a pretty simple thing. You simply need two things. You need to start off with a rectangle, and then you draw a circle for each subset. Now, how you place each circle is where you spend the majority of your time thinking about Venn diagrams. Circles can be inside of circles, circles can intersect other circles, but each circle represents a specific collection. We call that a set of something. And in a Venn diagram, you get to define what that is. Okay. How many of you have never seen a Venn diagram before? Okay, cool. Here's an example. The universal set will be people. So let's see, I need and the subset will be people who like beef. I need to start drawing here. So let's see, we need to make a rectangle. So here's my rectangle, horribly drawn. All right, and sometimes in that you'll see U for universal equals people, P for people, people. So this will tell the reader that what is inside here is not literally everything in the universe, but just people. And then we start drawing circles. Each circle represents a set of people. And there is no definition on how big or where you put the circle. It can go anywhere. So this is people who like beef. So beef. And then we'll do another circle for another condition. We'll say we have another circle for people who like vegetables. So here, after you draw your first circle, is where you stop and you think. Are there people who like both vegetables and beef? Yes or no?
Yes.
So therefore, our circles need to intersect. And this intersection, this area right here, would represent all the people who like, well, I didn't label this veg, who like both vegetables and beef, who like both vegetables and beef. So anything that inhabits right here, I would live right here, like both vegetables and beef. Anyone who sits outside here would be?
The ones that don't like beef or vegetables.
And anyone, where did my mouse go? My mouse has been disappearing on me all by itself. There we go. And anyone who lives right here, what?
They
Only
like
likes vegetables.
And anyone right here?
They only
Likes
like
cow.
And this is why Venn diagrams are so popular, because they literally are intuitively a very quick thing to learn and understand. And they also convey a whole lot of information, a whole lot of information. All right. All right, let's look at another one. So let's see, if this is the universal set are polygons, the subset is parallelograms. Well, we got three subsets. We're gonna have three circles. We're gonna have three circles. So let's see if we can do this one. So our rectangle, inside our rectangle, all we have, U for universal set, U is equal to polygons. Polygons. I'll just put poly. All right. And then our first circle, usually you adjust this as you're doing it. These are PAR, parallelograms. So these are my parallelograms. All right, what's my second set? Right angles. Are there any polygons with right angles that are also parallelograms?
Yes, rectangle.
All right, so they have to intersect. So this is 90 degrees. I'll just put 90 degrees. So these are my polygons with right angles. Now, I got hexagons in here too, right? Pentagons and whatnot, they could have right angles, but in between your parallelogram and or the overlap between your parallelogram and your 90-degree angles would be those polygons that are also parallelograms that have right angles. So those would be your rectangles, your squares. Did I leave anyone off? Your right trapezoids, any of those. Oh wait, right trapezoid is not a parallelogram. So yeah, right trapezoid would be over here, but squares and rectangles would be right here. My last one is a polygon with congruent sides. So can you have a polygon with congruent sides that also has right angles?
Yes.
So it's got to intersect that. Can you have a polygon with congruent sides that is a parallelogram? So therefore, this one has to intersect both of those circles. So you get this triple overlap right here, right? This is where all three circles intersect. Which parallelogram sits right smack dab there?
Square.
Square. Which parallelogram sits right here that's a parallelogram and it has right angles?
Rectangle.
And which parallelogram sits right here that has congruent sides? Which parallelogram has congruent sides?
Rhombus.
And let's see, which congruent sides are 90 degrees? Right here.
Square?
Let's see. This is a polygon with congruent sides and right angles, so squares. So we're saying squares is here and here. So actually, squares can inhabit this whole area right here. Okay. Cool. And the reason why they can do both is because squares are also parallelograms. Okay. So there's your example of Venn diagrams. Not too hard to understand. Well, it turns out that you can actually use Venn diagrams to help you prove things. It doesn't seem that way. So the easiest way for me to show you this is just to demonstrate it. So here's a statement: all runners are athletes. Can we agree that this is a true statement?
Yes.
Okay.
Yes.
Sure.
So that's a true statement. So if I were to draw this as a Venn diagram, well, people, runners are people. You could argue dogs are runners, but let's just keep our universal set to people. And it says all runners are athletes. How would I draw that as a Venn diagram? If all runners are athletes.
Wouldn't you put the circle, like a big circle, and then you have a smaller circle
Yeah, I
in the
would
big
have to.
circle?
So if all runners are athletes, then runners, that entire circle must be inside of the circle called athletes. Okay? So, well, there's a Venn diagram of this statement that's a conditional, if P then Q. If you are a runner, then you are an athlete, okay? So it turns out we can use this Venn diagram to answer both converse, inverse, and contrapositive. So Leroy is a runner. So Leroy is the conditional, if P then Q. So if Leroy is a runner, where does he live in our Venn diagram?
In the runner circle?
There. So what we conclude about Leroy is that he lives right there. So tonight for homework, they're going to ask you, what can you conclude about this Venn diagram? They're just asking you to say a statement. You know, think about where the dot would appear, and then make a true statement. Leroy is a runner and he is an athlete. He's also a person because he's inside the rectangle as well too. So he's a runner.
Leroy lived in Warcraft.
No, that's Leroy Jenkins. All right. Lucia is not an athlete. Where does she live?
In the rectangle, but not in the circle.
Right. So if you are not an athlete, is this a converse or is this an inverse? If you are not an athlete, here's the conditional, if P then Q. So if you are not an athlete, right, then this is the contrapositive. If you are not Q, then you are not P. So therefore, you are not an athlete. You must live outside there. So there's a contrapositive statement.
But that's not true, because Lucy could still run. She just doesn't use it for sports.
That's how we started this off by, can we agree that if you are a runner, you are an athlete? And you all agreed that was true. So if that's not true, then we have to change our Venn diagram, because then the runner would not be inside athletes. It would inhabit both. So if you want to make that statement, then we would get a different picture. All right, I'm showing you answers here. Darn it. Linda's an athlete. Where does she live?
In the athlete square?
Yeah. Now, she could be in the runner square. It doesn't say that she's not a runner. So this would be the converse statement. If you are an athlete, you are a runner. So the converse, if we flip those around, well, in this case, you could be a runner, you might not be. Because remember, even though the conditional is true, the converse is not always necessarily true. Linda could be a runner, but we don't know. And this is why, for the converse statement, sometimes saying it's false is very clear, and other times it's not clear, like in this case. So it's not always true here. So, I mean, sometimes we get a definitive, oh, no, that's not true. But in this case, all we conclude is that she might be a runner, she might not be one. Okay, does that make sense? Tonight for homework, they're just going to ask you true or false, though. All right, it says Larry is not a runner. Where does Larry live?
He
Outside.
lives either in athletes or outside.
So this is the case of the inverse. If we negate the P, right? So the inverse of that statement, not P, not Q. So if you're not Q, well, I don't know, because we don't know if Larry, it doesn't say that all it says is he's not a runner. So we don't know if the inverse is true here. So the inverse, if not P, I mean, that's what it says, Larry's not a runner, so that's the not P part. But we can't conclude the not Q part because he also could be, I don't know, weightlifter or something like that. You could be an athlete, but you're not a runner. So in this case, that's just one of those ones that we don't get a good answer to what is he? Is he an athlete or not an athlete? Well, I don't know, right? If you just tell me he's not a runner, I can't conclude it from this Venn diagram. So tonight for homework, you're going to have this. These are questions 11 and 12, asking you to make a Venn diagram for this. You guys think you can make a Venn diagram?
Yes.
Okay, cool.
Yes.
They're kind of fun. All right.
Yep.
Do you want to look at any of the homework ones, or you just want to try it yourself?
Try ourselves.
Okay.
I do have one question though.
Sure.
When dealing with equations and inequalities, how do you make them contrapositive and inverse?
Well, so you're looking at question number 1. So you're given an equation. It says if n equals 17, then 4n equals 68. So basically what you do is you solve the equation. See, that's how you're going to figure out if it's true or false. But for an equation, if you are equal, if you want to negate that, you would simply say if you are not equal. So for instance, on number 1, the converse to that would be if 4n does not equal 68, then the contrapositive would be if 4n does not equal 68, then n does not equal 17.
Okay, and what about inequalities?
It does not equal, right? I'm looking to see if there's an inequality. And
Number 9.
Number 9. Well, they're just asking you whether it's true or false.
But you have to state the statement, the contrapositive, converse, and inverse.
No, you're right. You're right. How come it doesn't? I'm looking at the answers in the book here, and it doesn't have that.
That's the one with the table you mentioned.
It is. 1, 2, 3. Table like shown. 5. Oh, I see. Yeah. Okay. So I kind of explained it incorrectly. So they just want you to put the words P and Q for each statement in exercise 5 through 10. Complete and copy a table like this one shown. I'm looking at the answers. They're just saying true and false. They're not doing that middle column right there. Okay, so to answer your question, how do you do an inequality? So for instance, the statement, 9 is the statement. So if negative 2n is greater than 6, then n is greater than negative 3. That would be the statement. Is that true? If n is greater than negative 3, well, basically you would solve the inequality. Remember, you flip the inequality, so you would get n is greater than negative 3. So that's true. That is a true statement. The contrapositive is, let's see, if n is not greater than 3, then negative 2n is not less than 6. You're going to have to actually do that math to figure that out. So just use the word not and you'll be fine. Does that make sense? Ben?
Yeah, it makes sense.
Okay. Yeah, the answers in the back of the book, if you look at, they don't provide the actual statement written as converse, contrapositive. They're just going to have true or false. That's kind of lame. They left off the entire middle column. At least in my teacher manual, they left off the middle column. They only have the true and false part. Okay, I didn't have anything else for you guys. That was 45 minutes. We're right on time to finish. No questions. You can certainly ask if you have one later on. I'll answer it. I stay up to at least 8 o'clock. Although tonight, 10 o'clock, PlayStation goes on sale. I might stay up a little bit later to see if I can snag one. We'll see. But if you do have any questions, just go ahead and send them my way, and I'd be happy to answer them. Catch you guys later.
Goodbye.